Hey there! In this video we are going to look at how replacing x with x plus or minus a number or y with y plus or minus a number in the equation of a function causes a horizontal or vertical translation in the graph of that function. Before we start talking specifically about translations, we should recognize that in general the word transformation when you're talking about functions refers to something that changes the equation and a corresponding change in the graph where the location or shape or orientation or any combination of those are changed. In mathematics, when you talk about functions, the term translation is a kind of transformation that refers to a shift in the graph of a function where it moves to a new location, but the shape and orientation don't change. A translation can be vertical, like that, or it can be horizontal, like that, or you could have some combination of the two of those things, and it can end up anywhere. First, we're going to look at vertical translations, and as our base function, we're going to use y equals absolute value of x, the function you saw a minute ago in the graph that I was moving around, and we're going to make two changes here. We're going to take that base function and change it to y equals absolute value of x minus 3 and to y equals absolute value of x plus 4 and see what happens with the values in the table here. Now, before we move forward, it's worth noting that you could actually write this in a different format. You could write this as y plus 3 equals absolute value of x, and you can write this one as y minus 4. That plus 4 could go over there as minus 4 absolute value of x. Now that's along the lines of what I alluded to at the beginning of the video when I said that we were going to be replacing y with y plus or minus a number like that. But we are going to stick with the given format because it's easier for calculating those values in the table here, the y values. Now if you go ahead and substitute the x values, we're using the same x values in each of those tables, and you substitute it in for x in each of those. Here's the y values that you get. Now in the first table, it's the values that you expect, just the absolute value of x, right? If x is positive, it stays positive, and if x is negative, it becomes positive. The other ones, what's happening is that same thing is happening. Say, for example, here you substitute in 2 into this. You put 2 in here, absolute value of 2 is 2, but then you're going to subtract 3 after you've worked out that absolute value, which leaves you with minus 1. The same goes here. Say for this minus 3 here, you put a negative 3 in there, absolute value is positive 3, and then you subtract 3, so you get 0. In each of those cases, you're subtracting 3 after you work out the absolute value. Or in other words, after you work out these same values here, that's what that's going to produce, and then you're just going to subtract 3 from all of them. So what you'll notice here is these values are the same as these values, except they're 3 lower. All the y values have been reduced by 3. And you see the same thing in the second table there, that all of these are, for example, again, if you put a 3 in, absolute value of 3 is 3, and plus 4 to that gives you a 7. Let's do one on the other side here. Negative 1, you put negative 1 in there, absolute value of negative 1 is positive 1, plus 4 is 5. And in a similar way, these y values are these y values, but 4 greater. You've added 4 after you've worked out those absolute values. So the change that you see there in those tables, for the middle one, for this one, you have that the y values are 3 lower for the same x values. And in the second one there, the y values are 4 higher. We're going to graph those 3 functions. Now you can go ahead and graph the points in the table and see what the 3 graphs look like. When we go and do that, in the interest of time here, this is the result that you're going to get. You're going to get that V shape 3 different times there, but it's going to be in a different location. It's the same shape, but in a different location there, right? You have your base function in this here, and you have these other two. So this second one, that's y equals absolute value of x minus 3. As we saw in the table, the y values were all 3 lower. And in this situation, the graph is 3 units lower. Every single point. This vertex here is 3 units lower. This point is 3 units lower. Every single point is 3 units lower on that graph. Right? Makes sense, because if you subtract 3 in your calculation process, your y values are all 3 lower. And the same goes for the second one there. If we look at that one, this y equals absolute value of x plus 4, all of those y values are 4 higher, right? Every single one. Again, this vertex is 4 higher, but every point on the curve has gone up by 4, because in your calculation process, you worked out the absolute value, then you added 4, so it makes sense that it's 4 higher than that. So if you're going to describe this here, what's happened in each of those cases, we have the blue graph, y equals absolute value of x minus 3. Y equals absolute value of x minus 3 has been, you say, translated down 3 units. And the other one then, as you can probably predict here, y equals absolute value of x plus 4, it has been translated up 4 units. And if you want a bit of an abbreviation here, what I tend to call this is I call this one a vertical translation, VT3 down, and this one up here, call it a vertical translation for up. We're going to look now at horizontal translations, and for this we're going to change it up and use a different base function, y equals x squared, that basic parabola that you probably have seen before. So we're going to look at that equation, and we're going to also change it to y equals x plus 3 all squared and y equals x minus 4 all squared. In the intro, I talked about this as changing x to x plus 3, replacing it, or replacing x with x minus 4. And we'll see what happens in these tables here. Now, for these tables, you notice that these x values are different, and in a second you'll see why that is. But first we'll generate the y values, and we're doing that just by substituting these values in for x in each of those. All right, so when you do that, in the interest of time here, you get those values right there. And as I said, the x values are all different, and why this is because to really see what's going on here, it's helpful in this situation if we choose x values that are going to give us the same y values. So these different x values here are such that we always get these same y values here. And to see that, so if you've seen this function before, you know that it's just x values and their squares. The y values are just the squares of the x values. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on, right? It would continue past there. And the same goes the other way, because when you square negatives, it becomes positive. Now, in the second case here, what we're going to do is we're going to add 3 before we square this thing. We're adding 3 before we square that thing. If we want to achieve the same y value, which was my goal here, if we want to achieve the same y value, if I'm going to add 3, I have to start with x values that are 3 lower than what I had over here. These values are all 3 lower than that. And similarly, for that second one, if before I square it, I'm going to subtract 4, and I want to achieve these same y values, if the first thing I'm going to do is subtract 4 before I square the number, I have to start with x values that are all 4 higher than these ones. You see that these are all 4 more than those ones. So just to summarize that there, when you replace x with x plus 3, what happens is for the same y values, the x values are all 3 lower if you replace it with x plus 3, and the x values are all 4 higher if you replace it with x minus 4. So it's a little bit strange. It works kind of the opposite. You add something in here, it makes these lower. You subtract something in there, it makes these higher. You may have seen that before too, actually. So we'll summarize it over here. To get the same y values, in that first one, x values are 3 lower, 3 less, and in the last function there, the x values are 4 greater, 4 more we'll just put here. Now we're going to graph these 3 functions as well. You can go ahead and graph the points from those tables of values. And again, in the interest of time, those are the graphs that you're going to get for each of them. And as you see on the graph, what has happened is a horizontal translation. This function here, y equals x plus 3 all squared, you noticed in the table that the x values were all 3 lower for the same y values. So what that means is for this same y value of 0, the x value is 3 lower, 3 to the left. And this one, where that x has been changed to x minus 4, this x value is 4 greater in order to achieve that same y value of 0. And the same is true for all of these other ones. Every single point in this, every single point on the graph moves. It's not just that vertex that moves, it's every single point, right? And on this, every single point here moves 4 to the right. This point here, 4 to the right, and so on. So what's happened there is that this, y equals x plus 3 all squared, has been translated 3 units left, and the other one, of course, then has been this one, y equals x minus 4 squared, has been translated 4 units right. And again, if you want some abbreviations there, I would call this a horizontal translation, 3 left. You can put an L or left like this if you want. And then this one is horizontal translation, 4 units right. So we're now going to try and take some of those concepts and apply them here to describe what change has happened in a graph and write an equation for that. So in this first one here, you notice that this is f of x. Now we're trying to write an equation for this. This is the transformed function. How do you get g of x from f of x? So you take f of x, if you look at it, just pick any point on the graph. It could be this one here. That point, the corresponding point on this graph, is right there. Or the corresponding point to that is right there, and so on, right? This one up here is right there. If you look at that, that is 5 units to the left. So that change is 5 units to the left. So if you're trying to describe this, you're going to say that this is a horizontal translation, 5 units left, if you're using my abbreviations. And if you're trying to write an equation for that, then the equation that you can write for the blue graph there is, you can say that g of x, an equation for g of x is, if you take f of x, now to shift it 5 units to the left, instead of having this x in here, we're going to replace that x with x plus 5, because if we put x plus 5, it goes in the negative direction there. So g of x is equal to f of x plus 5. In this second one here, you notice that every point on this graph, f of x, is shifted down, looks like 6 units there to get the graph of g of x. This has gone down 6 units, any point here, every point on the graph. I'm not going to draw them all, but all those points are shifted down 6 units. And so you're going to say that this has had a vertical translation of 6 units down. And if you want to write the equation of it, to get g of x, you take f of x. Now, to get f of x to shift down 6 units, you're going to put a minus 6 outside of the function here. When you make that change outside of the function, it's going to change the y values. So those are those 2 equations for that. We're next going to look at a situation where we have a given function, this graph here, and we're going to graph this transformed function here. So first of all, we need to recognize what those changes represent, what they're going to cause. So if you change x to x minus 2, that is going to cause a horizontal translation of 2 units to the right, because when you replace it with x minus 2, it does the opposite. The x values have to be 2 greater in our transformed function. And then we also have this plus 5 on the end, and that is going to cause a vertical translation. And this does what you think it does. It goes 5 up. When it's plus 5, when it changes y, it changes it the way you think it's going to change it. Plus 5 increases the value, and the horizontal one's the one that does kind of the opposite of what you think. So to be able to draw the graph, all you do is do those two changes to each of the points. Now you can just work with these sort of key points along here and transform each of those. So if you take this point and you go 2 to the right and 5 units up, it's going to end up there. And the same goes for each of these other ones. 2 to the right, 5 up, goes to there. And this one, same thing, you're going to find it's right there. And those last two, 2 to the right, 5 up. And lastly, this one, 2 to the right, 5 up. It's there. So when you're drawing this graph of this transformed function, I will try to draw the straightest lines I can here, but the computer doesn't always tend to do that. When you're using the pen, it makes them a little wiggly. That's not too bad. And connect those ones, connect to those ones. That is quite wiggly. Let's do that one again. Not any better, I don't think. There you go. So that's that function, and we can label it. We can call it y equals f of x minus 2 plus 5. Here we have a little bit more complicated looking function than we've had before. F of x is 3x squared minus 2x plus 1. And we're going to write the equation of the transformed function after two translations have happened. One that is 3 units to the left and one that is 7 units down. Now the first thing that we need to do here is establish what it is we need to do to the equation to get those two things to happen. Now this first one here, to get that to happen, we need to take our x and we need to replace it with x plus 3. To go in the negative direction, the left, we have to add 3 to x there. And to get it to go 7 units down, we need to subtract 7 from the function. So to make things a little bit easier here, I'm going to use the notation g of x to represent the transformed function. So to do that, I'm going to take f of x, but instead of x in here, I am going to replace that with x plus 3. And then on the end of the function, I'm going to subtract 7. So that's what g of x is there. So I can write an equation out using that specific function, this specific function, but instead of writing 3x squared, I am going to put in here x plus 3. And instead of writing minus 2x, I am going to write, instead of that x, I am going to put x plus 3. X appears in 2 places in this original function. You have to replace both of them to get this change to happen. And then of course I had the plus 1, and to get the vertical change to happen, I have to subtract 7 from the end of that function. So that function is the transformed function, but it probably helps if I simplify it a little bit. So we're going to write that g of x, if you expand this x plus 3 all squared before you multiply the 3 in, so I'm going to leave the 3 there, expand this x plus 3 squared, so x plus 3 times x plus 3 is x squared plus 6x plus 9, and I will leave this one the way it is for now. We can expand both of those together, and then I can actually combine these two right now. Plus 1 minus 7 is minus 6. And if we keep going here, now we can distribute this there, and so I'm going to have 3x squared plus 18x plus 27, and if I distribute this, I'm going to get minus 2x, but minus 2 times plus 3 is minus 6, and then of course I have this minus 6 still there. If I combine all my like terms to make it as simple as possible, there's only one x squared term, but there are two x terms, so plus 18x and minus 2x is plus 16x, and then I have 3 terms that can go together. The plus 27 minus 6 minus 6. 27 minus 6 minus 6 is 15. So that's the equation of the transformed function in simplest form. Now, just looking at the equation, it's hard to tell that that's what's happened once you've simplified it. But if you wanted to check to see that this is indeed the graph you get after this function, if you have graphing technology, you can put this one in and this one in and just confirm that the graphs are apart by 3 and 7. So in summary here about translations, when you have a function f of x and you change it to y equals f of x plus k, the graph undergoes a vertical translation. And that vertical translation is up if k is greater than 0, or in other words, if it's a positive number. And it gets translated down if k is less than 0, or in other words, if it's a negative number. And then when you have f of x and it's changed to f of x plus h, or in other words, if you replace the x with x plus h, that graph undergoes a horizontal translation. And the horizontal translation is to the right if h is less than 0, or in other words, if it's negative, and it is to the left if h is greater than 0, or in other words, if h is positive. So this is the one where it works the opposite of what you might think. When h is negative, it gets shifted in the positive direction. And when h is positive, it gets shifted in the negative direction. And then lastly here, translations of a function result in graphs where the shape and orientation of the original remain unchanged. The graph has shifted, but the shape and orientation have not changed at all. That's it.